started and people will trickle in the beginnings kind of announcements anyways.
Okay, sounds good. Okay, so hello again, everyone, for anyone who's joined the past couple minutes. My name's Sarah. I am a PhD student at MIT, and I will be your TA for this section for, I guess, the next couple months of the course. So the program for today is that I give like a little brief introduction on me, give some announcements for what this lab section is going to be like in the future. And then we're going to do both pre and post lab feedback to try to assess like where you guys are at, whether you need us to go slower or faster, if you're understanding the lecture material, etc. And then as well, the lab content in between. So here's my wonderful headshot. I'm originally from Houston, Texas in the US. And I guess this is a US only section, so maybe not super important to specify. I did my undergrad.
US only, Sarah. We have folks
really?
all over, including Costa Rica and I don't know, all sorts of other places, Mumbai, Canada. So yeah, folks from all over.
Great. Yeah, and I guess people are giving their intros in the chat. It's very nice. You can like shout out people. I see Pedro and Asal and Ramya and William, so many people. Yeah, thank you all for introducing yourselves. Yeah, and now I'm, like I said, I'm now at MIT as a PhD student. I work in the engineering quantum systems lab, where I focus on kind of mesoscale quantum information and like noisy intermediate scale quantum computing, mostly with regard to quantum simulation. And I work with NASA. They're over here, but I don't have them on the map. Yeah, okay, so I cannot get together the fact that my slides are on my iPad. So these are just the announcements for this week. You can read them and I'll go through them. We're not going to take attendance this week. We'll not be doing homework this week, but all these will be problems that you'll have to deal with next week on Canvas and for both. But we just don't have Canvas set up yet, so you don't have to worry about that right now. Also, Discord. I don't know if we have Discords for each lab section. I don't know if
No, not for each lab section. I'll drop the link in the chat for Discord. If anyone has not joined yet, that is where we will be sharing course information. So there will be very few emails after this, so please join. I'll drop it, and you have to get verified so you have access to the information. We will have specific lab sections on Canvas when we introduce that platform next week.
Okay, and so now we have a few ground rules just in general for this section. So I have wonderful Rachel as my moderator to help make sure that everything is good with moderating questions and making sure that I actually notice if you guys are raising your hands. The biggest thing is just please don't spam the chat. That is definitely, like, even with the moderator, that's really hard to get through. And I'm going to ask for your answers or your feedback on different things throughout the lab section. So please only really use the chat or raise your hand when that's happening. Don't just go the entire time. But we'll try. It is a large group, but we'll try to. I'll try to answer as many questions as I can with that. So we also want to try to encourage people that don't normally speak up in classes, whether in person or online, to ask questions as much as you are able to. And if you tend to ask a lot of questions, be mindful of how, if you are asking questions constantly, if you can encourage like your classmates to maybe like ask, if there's a similar question, encourage them to like ask that instead. So we won't be able to answer all the questions in lab sections because they are only an hour, but we will be answering them on Piazza and through Discord as well. So if you have any maybe more involved questions that you'd like me or another TA to go over, you can ask them there. And this is also like, this is the first lab, like the first lecture I know is very general to quantum computing, but we're mostly focusing on kind of the basics of classical computing, like doing binary arithmetic, basic logic gates, and kind of some complexity if we manage to get to that this lab section. So we're not going to go too much into quantum specifics after a couple weeks. Okay. So now I'd like to run a poll prior to the, I guess, ooh, okay, I can just launch it. Right, great. So I've launched a poll and we have the scale here. How well did you understand this week's content? And so there's gonna be like a pretty wide variety response. I'll leave that up for a second. Just so we can get most people's responses. I'm at, I guess, around 140. So that's pretty good. Great. So almost everyone has voted, so thank you guys for doing that. I'm going to move on in the lecture. I guess I can leave the poll open. And if you haven't responded yet, then you'll still have some opportunity to do that. So the learning objectives for this lab, so now we're getting to the actual technical content. If you were napping a little bit, now's the time to wake up. The primary goal of this lab section is to go over how binary numbers work, why we might want them, and do some basic conversions between binary and decimal. And then I'll also go over the basic logic gates used for classical computation, and I'll make a note of the ones that are, like, I guess, quantum compatible. And then if we have time, we'll do a design problem with a 1-bit adder and do a kind of basic little algorithm and go over the complexity of that algorithm and how maybe that would be different on a quantum versus a classical computer. So I know it's possible some of you have gone over binary numbers in some class before, but we're going to go over kind of from the very most basics. We have our decimal number. These are not the same number if you were concerned. Of, I guess, 147, we have this one, which is in base 2. So we can convert this, which we'll do on the next page, but something on the order of, I guess, 0, 1, 2, 3, 4, 2 to the 7, so like 100-ish. So the reason why we might want to use decimal numbers or binary numbers rather than decimal numbers is because of how a computer operates. Every single component in a computer can be represented just as a switch like this. So when the switch is open, that gives you a 0. When the switch is closed, that gives you a 1. And the reason for that is that when the switch is closed in a computer, you can have charges like electrons or whatever you want. This is a little bit in the weeds, so don't worry too much about this if you haven't covered electrons or kind of basic computer bits. This is just a bit of motivation. All you have to know is if the switch is open, you're not getting anything through this pathway, and so you get nothing out. Like, that's why we use a 0, as we're representing just nothing. If you just had this circuit and like no one had ever seen it before, like no humans ever seen it, but just know there's a switch there, you would get a 0. It's only when you apply or when you close this switch that you manage to get a 1. So that's the reason we are using binary numbers to represent all this mathematics later on in the course. And I'd like to give a little example for how to convert between binary and decimal. So if you guys wouldn't mind giving me some 1s and 0s to work with, you can just put them in the chat and I'll choose a couple. If the chat is still open. Actually, not sure. Great. Okay, I've gotten some private messages. Okay, nice. So I've gotten a bunch of ones and zeros. So I'm gonna choose just as many ones as I see from people. So I'm gonna do a 1, a 0, a 1, a 1, just choosing random. Oh, I think I see Audrey's happens to be exactly what I have so far. So I'm going to go the 1, a 0, a 1, a 1, a 0, and 0. And so to convert between binary and decimal, what we want to do is in the decimal numbering system, every time you get to a 9, you go up a digit. So a way you could represent this is like on a clock or a dial, where your 0 point is here, and you can put 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't have to number them. And then as you proceed around this, going to 1, going to 2, going to 3, going to 4. Oh, why is this? Oh, well, it's fine. Regardless, going around, eventually you're going to need another dial to represent how many times you've gone around this first dial. So we add another one, and then that's going to be at the first tick. Oh my God. I'm sorry, I have a bunch of messages popping up. I need to like silence my phone or my. I don't know what to do. Okay, I'll deal with that later. So, okay. Yeah, so with that dial analogy out of the way, what happens when we convert to binary instead of using decimal is our dial now only goes from 0 to 1. Those are your only two options. Okay. And so when we go around this dial, we go to 1, we go to here, this is already at 2, so we already have to start using our second dial to represent that we are at 1, and then maybe a 0 again to represent 2. We can't represent as many numbers with a single digit in binary. So the way that we convert between binary and decimal is the same idea as these dials, where since the maximum number that you can represent by a single digit is in base 2, we can number these digits from I guess 0 to 5. So we have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5. And so you can convert these from, like, you just raise 2 to the each power, which 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, and 2 to the 5 is 32. And if you can look up these tables online, or if you don't have this in your head, it's just, you're just doubling each number. So it's really not too difficult to convert between these. You don't have to do, oh, I need 2 to the 5. You're like, okay, I know 2 to the 3 is 8, multiply by 2, multiply by 2 again. And then when we want to add these numbers, we can get rid of the zeros, and we add the remaining numbers. So we have 32 plus 8 is 40, plus 4 is 44. And so that's just a very simple conversion between binary and decimal. Now, if instead we want to convert between decimal and binary, I'm going to choose a smallish number for ease of use, I guess. I guess if you guys would like to suggest a number, I'd like something under 50-ish, but can be over 10. See, Diana suggested 42. Let's start with 42. So to convert between decimal and binary, the easiest way is just to kind of successively divide by 2. So as we discussed previously, each digit in binary corresponds to something in base 2. So when we divide 42 by 2, we get an even number of 21. And we know that the first digit, so put this in red, the first digit of our binary conversion is 0 because we have no remainder here. So we don't have anything in like any 1 in the smallest digit, because that corresponds to something that's multiplied by 1. Now if we divide this 21 again by 2, this is going to be super clear. Yeah. Let me try to represent this a little differently. Sorry if this is making it more confusing. We're going to take 21 divided by 2, gives us 10 with the remainder 1. And so our second digit is a 1. And so what this means is when we have looked at, or when we are looking at whether the number that we have has a 2 in it, you can see that with this remainder here, because the second digit corresponds to things that are multiples of 2, or it corresponds to like an additional 2 in addition to the rest of the number. I don't know if that makes any more or less sense. If you work through it, I think it becomes more clear. So our next, we next have a 10, which we again divide by 2. It gives us 5. Now things that we put as a 0. We then have 5 divided by 2, gives us 2, remainder 1. And so that gives us a 1. We then have 2 divided by 2, gives us 1, so that's a 0. And then we have 1 divided by 2, which gives us 0, remainder 1. So our final number is 10101, or 101010. Yeah. And so this kind of successive division is the easiest way to convert between any 2 base numbers. And you can even do this in other bases if you want to try out in your own time converting to base 5. You can do the same thing, dividing some base 10 number by 5 successively. And the result is always the remainder of your division is going to be the next smallest bit. So that's kind of the trick, is you always want to make sure that you're going from the smallest number to the largest when doing this method, because you're ending up with, I guess, any overflow from your division. If you're looking at whether you can represent this number with only higher bits, or if you need to have a smaller digit to represent the number accurately. Okay, so now we're going to do some binary addition going off of the 2 conversions we did before. So if people want to give me some binary numbers, this is, again, pretty simple when you think of it as like a dial. So I have a bunch of options from Arsh and Evelyn and Maxwell and Osel and Min and Yash and tons of people. Thank you all for sending things. Okay, I'm going to just try to choose one of yours. And 101101. Okay. So when we do binary addition, we again have this issue where when we continue to go around this kind of imaginary dial that represents the maximum number of or the maximum value we can represent in a single bit, we immediately overflow, even just adding a 1 and a 1. So what we do is we do our carry bit up to the next digit. And so we end up with a 0 on the first column here. And then we have another 1 here. So then we have 1 plus 1, gives us another 0, another carry. Same thing here, another 0, another carry, and here, and here. Yeah. And finally, we end up with 11, or yeah, I guess 1.1 million, but in binaries, it's actually a pretty small number. So this is it's really simple overall to add in binary because you only have 2 options for what digit you can get out. You just have to be careful that you always make sure to carry your bits to the higher digits, even when you only are adding 1 and 1 and you don't think that you should have to go to another digit. Okay, so now I guess we have time for questions. So we're done with the binary portion of the lab. Next, we'll be going into some digital logic. Does anyone have any questions about the content covered so far? Ooh. Yeah, so here's the addition that we did. So yeah, I guess I kind of washed over how we can add an imaginary, or not imaginary, like a real line and just add zeros. You can always add more zeros at the highest point of any number. Like if you have 147, like we had earlier, you can represent it as 0147, and that's still 147. There's nothing in the thousands place. So you can do the same thing with binary. So what's happened here is we've added, we've added 1, 1, and 1. So this gives us 3. So we still have 1 left here, but we have another 1 that we then add to the next place up. And can you convert an odd decimal number to binary? I mean, I guess if we wanted to, where are we? Here. I mean, if I wanted to make this 43, it's a really simple trick. This is now a 1. So 1, 0, 1, 0, 1, 1 is equal to 43 in base 10. So that's, you just end up with something in the 0th place if you have an odd number versus an equal. And I guess I've seen a couple people ask, both here and on Piazza, about negative numbers or irrational numbers. And so you can represent all of these things in binary. There's one thing that the 2 things you should look up to learn about those are 2's complement, which is the most common method that people use to represent negative numbers using binary, and then floating point, which is the most common way of representing, I guess, decimal numbers or irrational numbers, or not, like numbers with like any kind of, like, I don't know, 10th place, 100th place fractions. I want to call them decimals, but that's technically not actually distinguishing anything, is it? Yeah, okay. Okay, so I think I've gone through all the questions. Yeah, I will just move on to logic gates, and there will be more opportunities to ask questions on Piazza or anywhere else if you guys have any. I just don't want to hold up too long. So this is kind of a very basic overview of any general logic gate. The idea, and logic gates can be a single input, but the most common, or the majority of them that we use commonly, are 2 input to 1 output, where you can have something, you can have some number coming into this input, and coming into input 1, some number coming into input 2, and you'll get something on the output. And so this truth table represents what we'll end up with when this happens. So let's say I put a 0 on input 1 and a 0 on input 2. Could anyone read this truth table out and guess what you think you're going to get on the output based on this table? Nice. I'm seeing a lot of ones. That is all correct. So yeah, it's really simple. You just read it straight through. If you are confused, just look at it again, and it should be very straightforward to read right out. So we have a 1 here. So similarly, if instead I put 2 1s on the inputs, I guess it's going to be, I can't even distinguish between people. Yeah, it's going to be a 1 again. So it's just going straight through the entire table. So now I'm going to go into some examples. We're mixing it up a little bit right off the bat, doing a NOT gate first, which is technically only 1 input to 1 output, but it's actually a little bit simpler. If we put in a 0 here, we get a 1 out. If we put in a 1 here, we get a 0 out. It just inverts whatever input you have. And this is a unique type of gate in that it's reversible. And so when you are looking at quantum computers, the NOT gate is the only classical, or technically there are like some more unique, but of the logic gates we're going to cover today, this is the only classical logic gate that can work on a quantum computer, because if you run it through one direction and then you want to reverse the operation, or through the opposite direction, you will get your original value out, and you will get all of the information out that you put in. And that is something that's very important for quantum computers, because you don't want to lose any information. That is like kind of the fundamental requirement of any quantum operation, is you cannot lose any information along the way. So the next gate is our first 2-bit gate, which is the AND gate. So it works the exact same as the truth table that we saw above. With now we have the 2 inputs and we have the outputs. So if we put in a 0 and a 0, we get a 0 out. We can go through the whole table. The idea, all these gates are labeled as something that you could say, like, if I have input A and input B, then I have an output. If I don't have input A and input B, then I don't have an output. So that's why when only one of them is present, you have zeros. So I guess I'll halt slightly just because I got an interesting question I think can be a bit unclear. So with each of these gates, every single input is a single bit. Thank you, Punk T, for your question. I think it is a very good point that we are doing single bits on each input. We can't put 2 bits on a single input. So that's actually what we're going to go into with the adder before, is that each the adder later if we have time, is that we are going to be adding 2 single bit inputs together, and then we'll have to chain adders like that to do the addition operation we did earlier with many bits. You need to have many gates. Each of these gates can only interact with 1 and a 0. Okay. So the next gate is the NAND gate. And can anyone guess what a NAND gate might be? We have all these circuit representations of it. So earlier, yeah, so it's literally just, we have the opposite of what an AND gate does. And that's what this bar on top means, is that we're inverting what was done, what this operation does. So every single output is inverted after the AND gate happens. So if we want to go through what we did earlier with putting a 1 in, well, we have A and B, so we get a 1 out, but then we run it through this inverter, and so we end up with a 0 as the final output. And that's this dot on the end is just kind of a condensed way of showing the entire NOT gate you see here. Yeah, and you'll see this in the future gates as well. I guess I also didn't mention this like multiplication symbol. Like you can also like read this out as if you multiply a 0 and a 0, you get a 0. If you multiply a 0 and a 1, you still get a 0. So you can also represent this kind of mathematically if you find that more intuitive. And that holds for the AND gate as well. So now we have the OR gate, which is represented by this little pipe symbol. Points if you can find it on your computer. It's not hidden, but you don't necessarily use it very often. And so we have this kind of shield looking symbol to represent the OR gate, and it works exactly the same as you would expect something that you say OR would work. So if I have A or B, well, if I have A, if A is 0 and B is 1, well, I have one of the two, so I get a 1 out. And this is not an exclusive OR, it's not, that is a different gate that we will cover momentarily. When we say OR, we mean that at least one of the two inputs has something there. Oh, did this disconnect? Oop, I'll reconnect this. Sorry, guys. Okay, great. Yeah, so again, like all these gates kind of follow from each other. And I can go through, I just get this a little bit too fast, but I think, I feel like since I already know how these gates work, I'm definitely biased. I'm like, oh, of course, it's just an OR, A or B. If one of them is true, or both of them are true, we get a 1 out. But if anything is a bit confusing, we can go over it again with questions. So now we're going to look at the NOR gate, and similarly to the NAND gate, we just have the OR gate with this bar on top and this dot at the end of the original shape. So if I put a 0 on input A, a 1 on input B, well, do I have A or B? Yes, I have B, so I have one of the two. That's good enough. I have a 1 out, then I invert, I get a 0, and so that's this line here. If instead I want to put both, okay, well, I still have A or B, I still get a 0. That's this line. It's all quite straightforward once you kind of have the time to process it. So if it doesn't seem totally straightforward now, I think just looking at it and trying to guess what you think you'll get out, maybe even chaining a few gates together, is a really good exercise because it's really easy to check. You can actually use online tools that will allow you to chain a bunch of gates together, and it will tell you if your answer is right or wrong. And you can just Google for those. I don't know if any of them sent out. Okay, and so now this is our final 2-bit gate. I always want to say qubit because that's normally what I work with, but these are regular classical bits. And this is the exclusive OR gate. So this one, can anyone guess what an exclusive OR might be? Ooh, I like Ariel's suggestion, an English OR, like what you normally associate, like, would you like cake or pie? You can't say like, oh, I'd like both. Like that's not acceptable under the English language definition of an OR. That is a very, very good definition, actually. So yeah, this is exactly that. You can only have one of the inputs be true. So I guess that's another description which we didn't really go into, but a lot of logic, which is called Boolean logic, a lot of times can be treated as an input can be true or false. The switch is open or closed. Do I have current? Yes or no. It's all equivalent representations. And so do I have something, or do I have an input on A or B? Well, if I only have an input on one, that's true. But if I have an input on both, then you can't have both with an exclusive OR. This is, I think, maybe even more intuitive than a regular OR gate because it more directly maps to how we think of things with language. Okay, so now I'd like to open it for some questions. I know that was a little bit quick because all the examples are kind of exactly the same, other than the numbers are different in the truth table, but the representations are all very equivalent. Ooh, okay, so I've got a very good question from Angela about how you physically go from an input of 1 or an input of 0 to an output of 1. So in a computer, you actually have a bunch of these switches kind of attached together in different ways, and they can be controlled. Like a lot of them are controlled switches. So I can try to draw like a little one. I have a switch here, and then I have, let's say I have like an extra little control line here. And so when the input of 0 comes in to whatever's controlling this, this will cause this switch to close. So you actually have like multiple switches involved for a single one of these gates. Let me, what other questions have I got here? So we're not going to go over any examples of quantum gates this lecture, but we will go through them in the future because that is a very like important part of the course is actually going through these quantum gates, but they are a little bit outside of the scope of today. Okay, so if that's all the questions, I'll give you guys like another sec. And actually, will these slides be shared with the students? Okay. So you will be able to like look at these after the fact. So no worries if you missed something right now. Okay. Okay, so now should I do the post lab feedback now or?
I think you made it through quicker, so you can continue with the optional content, and at like 5-2 we'll do the poll.
Okay. Sounds good. Okay, so now we're gonna do something fun with all the gates that we learned. And I will be going, kind of scrolling back to the gates just for ease of seeing them. So what we want to do is to design a logic circuit that will compute the sum of the two gates. So of 2 bits. So what we did earlier with adding like a 5-bit number, we're going to actually just add 2 bits because that's all we have space for with this adder. It gets increasingly complicated the more you do, but it does kind of directly map. So I guess I don't know if it's going to be unclear trying to do this in the chat, but if anyone can try to help me fill out this truth table, I'm going to go line by line. So we're going to try to add 0 and 0, and we're going to have 2 bits coming out of it. One is going to be the sum bit, which that's their first bit. And then the carry bit is going to be what we add to the next. So okay, a lot of you are pretty quick. Yes, it is 0, 0 when you add 0 and 0. So the operation we just did is 0 plus 0. We get 0, and then our carry bit, let's pretend like we already had zeros here. We just get another 0 out. Okay, so now we're going to do 0 and 1. So that is 0, 1, and we'll put zeros here. What are we going to get? Nice, I'm seeing a lot of 1, 0. Yeah, exactly. We're going to get a 1 out here. We're not going to get any carry. We're going to get another 0 here. So this is, it might be a little confusing because this is slightly inverted, where the way that you normally do math, we now have our sum bit first and our carry bit second, but we could just as easily swap them if we wanted to. Okay, Now we're going to do one more or two more, I guess. We're going to do 0, 0, or 1, 1 and 0 this time. And it's, guys, it's the exact same. So it's a bit anticlimactic. The really interesting one is actually 1 and 1. And what are we going to get out? These. Nice. A lot of you guys got it, or I think all of you got it, that you actually end up with a 0 in the first bit because we've now had to carry it over to the next one, and then we get a 1 here. Great. Okay, so now we filled out our entire truth table, and now we know what we want. So that's the first step of design, is you always have to know what you want to get out. And we can always check back against this if we're not sure if what we designed is quite right. And so here is the official result. It's the exact same as what you guys put together because you guys are so smart. So it's really not, we didn't even need this page. Okay, so the next step is where it gets a little bit more complicated, and this is very like dramatic. Like, I'm gonna stay up here. What we want to do is we want to create logic gates, or to choose logic gates that will end up with us getting these values out. So the first thing we're going to do is we're going to try to choose a gate that we think would work really well for this sum column. So what we want is if 0 and 0, we get 0, 0 and 1, we get 1, 1 and 0, we get 1, 1 and 1, we get 0. You guys are already just going for it. Yeah, no, thank you to Ayush and Thilak and Arvin, Emily, Alex, all of you, and even if you didn't mention it, but you knew it, I'm also impressed with you. This is the same thing as an exclusive OR. If we have A or B, well, with the 0, 0, we don't have A or B. With the 1, 1, we have A and B. That's too much. So we only have the English OR here. So what we want to do is we want to put an XOR here. Now, I think a lot of you already put the AND down to the second one, but we're gonna go through thing a little bit more slowly in case anyone hasn't followed. If we have 0 and 0 and we want to get 0 out, well, that kind of carries over to almost or to a lot of the gates. But the important thing is if we have a 0 and a 1, we want to get 0, and if we have a 1 and a 0, we get 0. So if we only have A or B, we don't get anything out. But if we have A and B, we get the 1. And you can look back at all the truth tables and see these are exactly the same. So this is exactly what we had in the sum column, and this is exactly what we had in the carry column. And you'll be able to look back and forth whenever these slides get sent out. Okay. So now what we want to do is actually draw this out. So we have our A, our B, and what we want to do is we want to route them to both of these gates. So I'm going to route this one to do our exclusive OR. It's a little ugly. And that's going to give us our sum. And then we're going to take this down, pop it over, and bring this to an and that's going to be our carry bit. This is all very, 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 very simple. I have heard someone say, talking about fanning out A and B. I mean, I'm just wiring them together, but there are more complicated representations you can use to describe the same operation. Okay, so now we have our wonderful result. It happens to be the exact same as what you all came up with because you're so quick. And now we're going to go really, really quickly just into a very brief overview of algorithms and the idea of complexity of an algorithm. So an algorithm is just a fancy way of saying a way to solve a problem. Like if you're making a recipe for something you're cooking, you could treat that as an algorithm. You have a bunch of inputs, you have a bunch of steps that you need to take with those ingredients, and then you're going to get an output, maybe a cake. It's the exact same idea with an algorithm on a computer. And you could probably make a fake cake on a computer if you wanted to. So for this algorithm, we're going to use an example. We're trying to find a student with a particular age out of a long list of students, and I'm first in the list for some reason. Can anyone think of a way that you might go through this list? And I'm getting some good ideas for ways that you could definitely speed this up. But if you want to keep this list unsorted and just find only the person that is 19 years old. And I got a couple of great answers. Yeah, so I've got a lot of actually, like, you guys definitely have done some computer science before. The idea for what we want to do is just, you can sort it with a variety of different sorting algorithms and then do a quick type of sort of that list. Or if you just want to keep it unsorted, you can go through each student and ask, like, is this age, like, I guess, we're going to do double equals. I'm sorry, my handwriting is so bad on this. And then get a no. And you just kind of go through each step. And when you do this in a computer program is, of course, you would have the computer loop through each index and ask this question. And then eventually you get down to here, is the age equal to 19? Yes. So what I want to ask for this kind of algorithm, where we're just going through this list and going through every single index on this list, how do you think this scales with the size of the list? And that is kind of the question for the complexity of the problem. And so again, getting a lot of people have clearly taken some computer science before, where it's often described as O of something. So in this case, it is O of n, where n is the number of students. So this whole length is n, because we don't know where Brian is in this list. Brian could be at literally like index n, like at the very last one, or technically in -1 if we're starting from 0. So this is okay. It's not going to take us that long to get through it. There are faster algorithms that are O of log n that are faster, but O of n is generally considered pretty good. What you really don't want is O of e to the n. And this means that it scales exponentially with the number of inputs. And that is actually what most quantum problems do. And that is why quantum problems are a problem. As you increase the size of your quantum system, you're scaling exponentially. So it's really, really quick to get beyond the memory of your computer. The example that I always hear is if you have, I think, 40 qubits connected together, or like 40 like quantum states connected together, you are already at the amount of memory of the entire Library of Congress of the US. And that's ridiculous. And then every operation also scales with, like, exponentially with the number of states. So it's just completely infeasible to do on a classical computer. So this is just kind of going over what we already said, but I'm gonna go back to where I had the student feedback, and I'm going to ask you guys to do the poll, and then we'll also concurrently do questions, because we have solidly 6 minutes with 2 minutes to spare. Yes, Audrey, that is exactly correct. That is exactly why quantum is really dangerous for current encryption, because current encryption is kind of built with like what you'll hear from like encryption experts is that nothing is uncrackable. It's all just like inconvenient to crack. So if you have something that's going to take like a couple months to get through, like maybe someone won't bother, maybe you can shut them out of the server before they manage to get into whatever like data that you're trying to hide. But with a quantum computer, it can do that exponentially faster. And so it's going to take them a day, like they might as well. Yeah. So I've gotten a question about how prime numbers relate to encryption. That is really just how a lot of encryption protocols work, where they use prime numbers as like kind of a mathematical trick to create these long, unique strings of numbers. And because if you're building off of primes, you don't have a base that's like divisible by a lot of numbers. And so it slows down the ability to find a specific like code if you use primes. That's definitely like in the math section. Okay, sorry, yeah, I guess the poll took a second to get going, but it's all good now. I'm glad that you guys are like understood this lab. I wasn't sure if I was going a little fast, but I was told that you guys were pretty smart, so I shouldn't go too slow. And no worries if you didn't quite get everything. There will be tons of more opportunity to learn about it on Piazza, to review the material, and I'm very confident in your ability to catch up. Okay. Okay, so I've gotten a question from Evelyn about whether it'd be hard to make quantum computers. Yes, it would be. That's why quantum computers will probably only be used industrially for specific applications that need this level of computation. Your desktop is probably never going to be a quantum computer, but I mean, 1,000 years out, who knows? But right now, they tend to operate at very low temperatures. Oh, of course, it's managed to disconnect again. Not that we need it. Okay. I've got a question from Dennis about current encryption key standards and how many coherent qubits would be necessary to factor it's like a SHA encryption. I don't actually know how, like it depends what's practical. We don't currently have really an ability to crack current encryption with quantum computers just because there are so many errors still. But I would assume something on the order of like 30 to 40 would probably be sufficient. I've heard a few different numbers, like on the order of like 10s to like 100, but like pretty much less than 100, you should be able to crack any of these like current encryption standards. I've gotten a question from Mo about the addition algorithms. They use the same set of logic gates for each pair of binary digits or separate gates. Oh, yes, you have a single line for a single like voltage, true, false, whatever, going into a single gate, or you have like your two lines going into a single gate and then your one output. You can't have multiple lines connected to a single gate and have that work. Because what's happening on the computer level is you just have a voltage where you have a 0 or a 1. And if, I guess I'll do like a backwards little switch. You can't have 2 on one level, otherwise it will just be in the noise bound. And the way that most computers actually work is they have like some voltage. I guess we need this. They have like a voltage plot where maybe you have some like oscillations in your signal, but you're like roughly at 1. Normally they just put a dead zone in the middle, like here. And this is called floating. I spelled that wrong. where you just don't know what it is. And then down here is 0, and up here is 1. So that's how they distinguish between things in like regular computers. I've gotten a question from Arsh about how quantum bits are represented, and that is actually something we're going to be going into very soon in the course, I assume. I don't know exactly what week it is, but we normally use a kind of 3D representation of a block sphere rather than this kind of 2D dial I showed you, where it can just be like a 0, 1, go around. We instead use a sphere where it's like this. And like we have like our X, our Y, and our Z here. And that is how we represent quantum bits. And they can be anywhere within this plane. And the phase is the really interesting part of quantum bits. And I will never stop talking about phase. The whole idea of coherence is all about the phase, which is pretty much where you are in this XY plane here. Okay. Seeing some questions. I guess, we're actually like down to the last 2 minutes, so I think we might have to send any of these. I know there's some good chat in here, so I'm glad you guys are like learning things from each other. Yeah, Rachel, if you'd like to give your blurb at the end.
Sure. Yeah, thanks, Sarah. Just a few super quick things, folks. I am about to drop the Discord link in the chat. Please, if you have not yet downloaded and gotten verified on Discord, please join that. You will start missing important course information. So it's really important. Find me on Discord and let me know if you're having any issues. Also, one other small thing. So as you all know, lab attendance is required. Lectures, we know students are tuning in from literally around the world. Those are recorded. So the Sunday 2 to 4 sessions you can watch at your convenience. We hope you will tune in live. But if you can't, we totally understand. We're not taking attendance there, and they'll be posted in Discord. For lab, you have to be here each week. The policy is 2 unexcused absences. So you don't have to tell anyone. It's a pretty flexible policy. Again, as we've said, the grades are in this class are just to hold you accountable and to keep you continuing to come to class and learning and engaging. So we're not trying to be punitive. We just want to make sure you're here each week. In the future, we will use Canvas, so the platform, kind of the portal that will host all of the course materials. We will use that for attendance. So you'll do a very similar poll, just like the one we did on Zoom today, but you will do it in Canvas and it will be linked to your student ID, and that's how we'll take attendance. So that will happen in the first 5 to 15 minutes of class, somewhere in that window. So please be here on time. I know some people joined like 20 minutes ago. So the class will always be at the same time, 8 to 9 p.m. Eastern. Please arrive on time if you want your attendance points. And just quickly, the question in the chat, the homework will be also submitted on Canvas. So it will either be like a multiple choice question, or you will write in the answer, and it will be automatically graded by Canvas. And you will have unlimited submissions, so you can continue to try to improve the grade on the homework assignment if you want. Again, it's about you learning. It's not about like trying to get A's and being competitive with one another. So you will all be successful in this class if you keep trying and showing up. If there are any administrative questions in the chat, I'll only take 1 or 2, but feel free to ask them. It is not a PDF. So again, you will submit the answers directly on Canvas. You won't be uploading a document. For this week, as we said in lecture and on Discord, you will not be submitting anything this week because you haven't gotten information yet about Canvas. You will submit the answers to this week's homework and next week's homework next week, so on October 31st. Eventually, not yet, but eventually your grades will be viewable in Canvas as well. the UC application. If you have questions about course credit, find us on Discord or email student@qubitbyqubit.org, and we'll answer the questions there. And yes, as always, all of the content for the rest of forever will be recorded and made available to you on Discord or Canvas. So slides, recordings, all of that. So nothing to be worried about, but be patient. It might take a day or two. I think that's it. Sarah, if you want to wrap us up, all good on
Yeah.
mine.
Yeah, thanks for giving the overview. I think that's all I have for today. So I hope you all have a good week. And next week we'll be going into some more, I think, vector math and maybe a little bit more quantum. Okay. Thank you all for coming.
Thanks, everyone.
Thank you.
Thank you. Thank you.
Thank you.
Okay, have a nice day. Goodbye.
See you next week.
Yeah.
Thank you.
Oh,
Thank
geez,
you.
mates.
Thank you.
Thank you. Goodbye.